Hi all, today we will continue understanding the connection between isoperimetry and concentration of measure. So last time we showed that there was a certain concentration function that we defined which was given by in any probability space endowed with a metric. We try to maximize the probability of the complement of a T blow up of any set A which has a significant probability measure, namely probability measure half. We basically saw that if we can control the concentration function alpha of T, then it actually serves as a very convenient upper bound to the probability that Lipschitz functions f of a bunch of random variables on that probability space concentrate around their medians. Okay, so it gives the alpha of T concentration function can give bounds on the deviation probabilities of Lipschitz functions about their medians by an amount of T. We also saw that bounds on alpha of T can be obtained by leveraging, whenever possible, exact isoperimetry results, which basically tell you what are the optimal shapes with respect to achieving best possible surface area for a given volume or vice versa. So exact isoperimetry results imply bounds which are often explicitly computable for the concentration function alpha of T. So for example, for the uniform measure or probability distribution over the surface of the unit sphere Sn minus 1, we saw that you could get a bound of alpha of T less than equal to e to the minus n minus 1 T square by 2. And likewise for Gaussian measure in n dimensions, we saw that alpha of T was upper bounded by e to the minus T square by 2. But the unfortunate fact is that bounding alpha of T using exact isoperimetry results is not always easy. It is however easier to get bounds on alpha of T without exact isoperimetry results, and we will exhibit some of these techniques here. So the next section that we will start with is called isoperimetry and bounded differences, and this is about understanding how to prove or control the concentration function by exploiting bounded differences properties. So for the purposes of this section, it's convenient to consider a function f which has a bounded differences property defined on a space xn, in that fx minus f of I is at most the sum of ci times indicator xi not equal to yi. We also call this the c weighted Hamming distance, and in fact this bounded differences property implies that f is Lipschitz under dcxy. So this means that if we can control alpha of T for the distance measure dc, then this will imply control of the deviations of f of x around its median by Levy's inequalities. So here's a representative result in this direction. It says that given a vector of bounded difference coefficients C1 through Cn and a set A, any set A, subset Xa of this metric probability space endowed with a product measure. So we assume that x1 through xn are independent random variables, not necessarily identically distributed. Then we have this inequality that says that the probability of the set times the probability of deviating in c weighted Hamming distance from that set by a quantity at least t is at most e to the minus t square by 2 L2 norm of c the whole square. Okay. And if we assume this theorem, it has some interesting corollaries. So the first corollary here is what happens when you have dcxy as the distance measure. It basically means that alpha of T, which was defined to be the supremum of the blow up supremum of the probability of the complement of the blow up of alpha by T of A by T, when probability of A is at least half. So here this probability of A is at least half. So you can use the theorem to get the further lower bound on the left hand side of half times this probability here, and then move the half over to the other side to immediately get alpha of t as being upper bounded by twice e raised to minus t square by 2 norm c the whole square. So for the c weighted Hamming distance metric on a probability measure space with independent measure, we already have, using the theorem, that we have an upper bound on alpha of t of this order, and this immediately implies further that for f satisfying, for a function f which satisfies bounded differences with coefficients c, we have median concentration. We have that the max of both these quantities z exceeding, so let me just say f of x exceeding m f of x, which is any median plus t, and as well as f of x being at most m f of x minus t. These probabilities are both upper bounded by twice e to the minus t square by 2 c1, twice the sum of the squares of the ci's. So this is the first corollary. The second corollary is something familiar to people in information theory, which applies this theorem to a special uh, weighted Hamming distance, which is the classical Hamming distance. So for Hamming distance dhxy, which is just tcxy with c equal to all ones, we have that the probability of dhxa exceeding nt. So this so we move the probability of a term all the way to the other end and then take exponent and log to get the following: e raised to minus n t square by 2 minus 1 over n log 1 by the probability of a. Okay, so this is the blowing up lemma is basically a corollary of this theorem when you specialize to the specific DC function where all the coefficients are the same. And a further consequence of this is the more useful part of this lemma in information theory, which says that information and coding theory, in fact, it says that if you are given a sequence of functions, given a sequence of numbers beta n that decay to 0, then one can construct sequences Tn and delta n that go to 0 as well, such that the following holds. Sorry, so I should probably be careful. So supposing that beta n is a sequence going to 0 with probability, so if there is a set A for which the probability of A is at least e raised to minus n times beta n, with beta n going to 0, then there exists, you can also find sequences Tn and delta n going to 0, such that the probability that dh, the Hamming distance of x from A, exceeds ntn is at most delta n, or equivalently the probability, you can state this equivalently as the probability of the ntn blow up of A, in our notation A ntn, has exceedingly large measure. Recall that delta n goes to 0. So This is basically saying that in words, what does this lemma mean? In words, this blowing up lemma says that uh, P of A, so imagine that there is a sequence beta n going to 0, that makes probability of A have a probability that can actually go to 0 but at rate which is slower than exponential. So P of A is about e to the minus n beta n, which is very small. A can have a very small probability, but the probability of A enlarged by ntn is suddenly extremely large. It's very close to 1. So by blowing up a very small set, uh, you can get by a very small distance amount, which is ntn, where tn also goes to 0. So you can, by blowing up A, by expanding A to cover a distance, extra distance of n times tn, which is vanishingly small compared to n, the maximum Hamming distance in the set, you could actually inflate the probability or blow up probability from very low, almost 0, to almost 1. Okay, so what is the proof of this second part? Well, the second part is just obtained by taking so you can do the calculations. You could basically take choose Tn, so choose delta n as 1 by n, and Tn, the required Tn that gives you this is square root twice beta n plus log n by n. You can check that this choice will basically give you what you want. Notice that ntn is essentially of order square root n, is roughly order square root n. So it says that if you blow up a very small set in distance by order about square root n, then you basically get extremely large probability coverage. And this property is heavily exploited in information theory, particularly for showing what are called strong converses and other coding theorems. Okay, so these are two immediate corollaries of this result of this theorem, that basically bounds the product of the probability of A into the probability of the complement of a t blow up of A by e raised to minus t square by 2 norm c the whole square. So let's in the remainder of this lecture, we will go ahead and prove this theorem. Recall that we want to show the following inequality, where the measure P is a product measure in the in the overall metric probability space. So towards this, let's first show an intermediate result. Let's assume we can show the following intermediate result. That the probability of dcxa exceeding t plus square root norm c square by 2 log 1 over pa is no more than e to the minus 2t square by norm c square. So let's assume that we have somehow shown this result that we will call star. Now assuming that star is proven, what we can do to complete the proof of the theorem is we first denote, so denoting u by this quantity, the square root c norm c square by 2 log 1 by pa. We have that whenever t is at least u in the above, so we can write probability dcxa exceeding t. So we add and subtract u from this t here, t minus u plus u. So we write this as, sorry, t plus u minus t, sorry, add and subtract u. and we have e to the minus 2t minus u the whole square by norm c square. That's what the equation, that's what the inequality labeled by hash gives you. And we can also show a simple lower bound that t minus u the whole square is at least t square by 4 for all t larger than 2u. So with this we will have that probability of dc xa exceeding t is upper bounded by e raised to minus t square by 2 norm c square. The 2 has gone into the denominator in the exponent just because of a division by 4, and this is true for all t larger than 2u. Now on the other hand, if t is less than 2u, then by the definition of u here, this is equivalent to the fact that the probability of A is at most e to the minus t square by 2 norm c square. So regardless of whether t is larger than 2u or less than 2u, for all t greater than 0, if you multiply these two probabilities out, so when t is larger than equal to 2u, the second probability is bounded when is very small. When t is less than 2u, the first one is very small, so you can bound the other probability by 1 in each case, and hence you get e raised to minus t square by 2c square. And so that completes the proof of the theorem modulo this inequality star. Now all that remains is to prove the inequality star for the C Hamming distance, C weighted Hamming distance. So the proof of inequality star. So how do we do this? In fact, we will accomplish the proof of star using McDiarmid's inequality. Which is essentially a statement about concentration about the mean. So interestingly, by the corollary of the main theorem, concentration around the mean finally has its consequence as one of its consequences as concentration around the median. Okay, which is a nice fact. So how do we use McDiarmid's inequality? Let's first define the quantity. So we are given a set A in the theorem in this inequality that we have to prove. So let us define g of x just as we did with the converse to Levy's inequality as the distance, the c distance of x from the set A, which in fact you can check satisfies the bounded difference property with coefficients c. Okay, this is something that you can easily check. The proof relies on using the triangle inequality for metrics. So with this, by McDiarmid's inequality applied to the g function, for the left tail, we have that the probability that dcxa is less than its own mean minus t. So this is for all t greater than 0, is at most e raised to minus 2t square by norm c the whole square. So one can take in particular t as exactly equal to EDCXA, expected value of DCXA, which gives you in particular that the probability that DCXA less than equal to 0, which by definition is just PA, is bounded by McDiarmid by e to the minus 2 twice expected value of DCXA whole square by norm C square. This is the same as saying that the expected value of DCXA, if you invert this expression, is at most the square root of C square by 2 log 1 by P of A. Okay, and now we can use the other direction using the right tail side of McDiarmid. For the same function g, you basically get that the probability of DCXA exceeding its expected value by an amount t is upper bounded by e to the minus 2 t square by norm C square. And finally, if we combine both of these results, so finally we get that the desired probability in star on the left hand side is the probability that DCXA greater than square root C square by 2 log 1 by PA plus T. So we know that this quantity here is already an upper bound to expected value DCXA. So we have that the probability is upper bounded by whatever you get when you replace the square root term by EDCXA, and the right tail bound is exactly what gives us the bound here from McDiarmid, and that completes the proof of this theorem. So basically we have understood the connection between what bounded differences functions mean and how functions of bounded differences functions of independent random variables enjoy both mean concentration via simple McDiarmid as well as median concentration thanks to bounds on the concentration function and Levy's inequality. So that finishes this lecture. Thank you.